we sort of don't know. There is some nonlinear phenomenon of collapse and revival, which it's a very well-known phenomenon in the Jains-Cummings model. But if you insert disorder, there's only one relevant parameter in the system, and if that parameter is disordered, then this phenomenon of collapse and revival will get wiped out. Roughly the same thing happens for entanglement. Let me not go into the details there. It actually, the collapse and revival vanishes, but importantly, the entanglement, it actually becomes almost a constant, but it becomes a constant of very near the maximum value, which actually can be a very useful thing for this system, because if I want to use this system in a quantum device, and if in that device entanglement is useful, then putting disorder can be useful, because the entanglement will not change in the averaged value. Whereas if you look at the corresponding thing in the pure case, in which there was no impurity, the entanglement does reduce much more. See, and this number is much higher than what I show there, and what I show there is closer to this value, and here, and you see that there are still, it can go down very much. This is 1 and 0, whereas in this case, this is still 1 and 0, and it remains almost a constant, and the oscillations die out as you go higher and higher times. This is one of the results that I want to advertise. So, that even after all the oscillations in the population inversion have died out, the atom-photon entanglement continues to appreciably oscillate. So you see that there is almost nothing here, but there is some oscillation here. And the other thing is that there is this oscillation dies out to give a very large amount of entanglement, whereas in absence of the impurity, there are much reduced values of entanglement also available in the system, which can be detrimental for a quantum device to work. So I'm not showing you the pictures, further pictures anymore. We have considered other types of distributions, not only the Gaussian disorder, but also uniform disorder and even discrete disorder and Cauchy-Lorentz disorder. And their behavior can be very different. Different types of disorder can actually induce significantly different behavior. There does not seem to be a very universal picture here with respect to the introduction of disorder.
Ujjwal, can I ask you a question?
Yes.
So what is the physical, if I want to connect it, so what does disorder do such that the population inversion, actually this collapse and revival, they kind of get impeded, or rather, as you increase the strength of disorder, what causes physically this collapse and revival to sort of go down?
Yeah. So, well, the short answer is I don't know. I mean, the point that I want to say is that this going away of disorder happens in almost all the disorders that we have seen. Where it goes away, that value changes. Yes, that and how fast it goes away, that value changes as I change the type of disorder. Mm-hmm. And so my initial thinking was that maybe the averaging that we are doing is reducing all the physical quantities, and everything becomes classical, and so there are no collapses and revival and so on. But then if you look at the atom-photon entanglement, you see that it gives you a nearly maximally entangled state with not a very high disorder, and as you go far away in time. So I sort of don't know. There is some nonlinear interplay here between the averaging and these quantities. As I said, the short answer is I don't know.
So in a condensed matter system, say in an interacting system, I'm not even talking about many-body interaction, but the short answer, or rather, intuitive way of understanding is that disorder creates more channels, more sort of modes through which the things such as maybe say resistivity or conductivity dissipates.
Exactly. I completely agree with this. Yes. Yeah. Tell me.
Yeah, I mean, I'm sort of trying to think that you have a atom-photon kind of coupled system. So this disorder must be creating some additional, just like what happens in a semiconductor. When you dope it with impurities, it just produces either N-type states or P-type states, depending on what kind of impurities you dope with. So these are some some states or some modes being given to the system.
Exactly.
So system interacts with that, and I'm just trying to think aloud.
Exactly. So this is actually, you are completely exactly what I thought first by looking at this left-hand picture. So the student came to me with this left-hand side picture, and this I said that, well, this is something that is expected, and you see that the system has more ways to dissipate, and the collapse and revival phenomenon is probably needs some sort of a coherence in the system, and that coherence is being lost by that channel of the disorder.
Yeah.
But then if you look at the entanglement in the system, is the completely opposite picture that you get. Because the entanglement in the non-disordered system, in the ordered system, did oscillate much more. It went to much lower values, whereas here it is going to a very high value.
Yeah.
In our experience with entanglement in a control system, is that it usually dissipates as you go far in time. And now we have put in a disorder that is another way to dissipate, and it does not seem to fit into that picture. It does not go near zero, it actually goes near one. So I agree that the channels for more channels for dissipation does fit into the picture if you look at the left side. But on the right hand side, it seems to does not fit in the picture. Maybe I don't understand it as yet.
My question was exactly that. I mean, intuitively the left picture fits, but the right picture somehow is exactly. Counterintuitive or something like that. Yeah.
Exactly.
Yeah, go ahead, please.
Yeah. Thank you very much. But this was a very nice question. I should have mentioned it in the slide. Yeah. Yeah. So this, as I said, that we did consider other disorders. I don't want to show you those pictures. Those are more sometimes can be more difficult to analyze than this. This one is Gaussian, so it's much easier. And if you and the quenched averaged atom photon entanglement for Gaussian and non-Gaussian, well, this is one picture. So this is something that I already showed you. This is the discrete. See again this, and this is the uniform. As I said, that I don't want to get into the detail. Here it's slightly more complicated, and this is one is Cauchy-Lorentz. But this same thing happens again and again, that it goes closer and closer to the one as you go for higher time. Slightly different for the uniform disorder, but for the others, this is what. Okay, so that is all that I wanted to talk about for the single Jains-Cummings model with disorder. One can certainly consider more complicated types of disorder and more different types of physical quantities, but we considered only those two. So I now want to go to something that is called the double Jains-Cummings model. And this is also something that is well known in the literature, in the literature of quantum optics and cavity physics, but also in quantum information, because due to this phenomenon that was discovered some years back, not by us, by other people, it's called something called entanglement sudden death. I'll tell you what it is. So this is the model. Well, it looks more complicated than the one before, but it's essentially the same. Okay, so it's only if you look at this thing in the bracket, this is what was there in the single Jains-Cummings model. We had ignored this part and this part because we were working in the interaction picture, and there is another line for the other cavity. So there are two cavities, and there is no cavity-cavity interaction, and there is no atom-atom interaction also. We did consider those. I am not advertising them, but let's fix our attention only on this simple type of a model. So there are two cavities and two atoms in them. There is a cavity-atom interaction for the first cavity, and there is a cavity-atom interaction in the second cavity. Okay, and we are calling them as A and B, the two atoms in the two cavities. Okay, and for simplicity, let us consider this as the state of the two atoms. So this 1 and 0 are the two levels. This alpha is a parameter that I assume that I can control. By the way, this alpha essentially controls the amount of entanglement in this atom, in this atomic state. And this is a picture not from us. It's some years back. I don't know whether I forgot to put the reference. It's by Eberle and other people. So this axis is time. The horizontal axis is time. The vertical axis is entanglement. It's some type of entanglement. It's called concurrence. There are many types of entanglement, and one of them is what the pictures that I showed before is a different type of entanglement. Here, this is a different system. As you see, as the system proceeds, the atom-atom system becomes a mixed state. Whereas in the previous case, it was always a pure state, the atom-photon state. Whereas here, we want to consider the atom-atom entanglement, and that atom-atom state becomes a mixed state as time goes by. And so we had to change, because of certain more technical reasons, we had to change the measure of entanglement. And the measure that we use here is called concurrence. It was given by Wouters and other people. The important thing that I want to focus here is that if you look at this point here on the time axis, so the entanglement comes down and discontinuously goes to 0 with respect to the time axis. So if you take a derivative of entanglement with respect to time, you will see a jump here. This phenomenon was called entanglement sudden death. This picture is for different values of the coupling constant. So this GA and GB are these values, this GA and GB here. So if you assume different coupling constants in the two cavities, then the picture is slightly more complicated. This is the picture when you have equal coupling constants. But in both, you have this sudden death of entanglement. This sudden meaning that it discontinuously goes to 0, and not discontinuously in the sense that discontinuous in the derivative, yes. So it suddenly goes to 0 with respect to the time axis. Fine. Now, we put in Gaussian disorder in the system. So this is the delta A here. So what I'm doing, and this is the delta B. I have considered both as Gaussian with mean 0 and standard deviation 0.1. And these are, if you remember this figure, so this are inserted. Instead of GA, I put GA multiplied by 1 plus delta A. And instead of GB, I put GB multiplied by 1 plus delta B. And those delta A and delta B are my disorders. So here there are two types of disorder. They are independently inserted. So they are independent Gaussian distributions. And then I do this evolution for given values of delta A and delta B from these distributions, and then average over them. And that averaged value is plotted on this axis, on the vertical axis. On the horizontal axis is still time. And I do it for different types of different strengths of the disorder. The disorder strength can roughly be considered as the standard deviation of this disorder. So here it's 0.1 and 0.1. Here it's 0.5 and 0.5. So it's more disorder. Here it's an intermediate thing. It's 0.1 here, but 0.5 here. What I want to let you see, want you to take away from this picture is that there are instances, for example, with this disorder, there is no sudden death anymore. So there was this going to zero suddenly. That suddenness sometimes vanishes even when it goes to zero, like here in the bottom picture. It can be completely obliterated. The entanglement sudden death can completely go away with the introduction of disorder. And sometimes it can remain, but for larger times it can vanish. Whereas in the previous figure, you see that it doesn't vanish with time. It keeps on continuing. It always has this, it oscillates, it's a periodic thing. I mean, this is also periodic. It goes here, but only the period is larger. So here, the same thing appears after the 10, which I am not showing. Okay. But here, this is not the case. This oscillation that is there initially doesn't come back. It vanishes. The actual value of entanglement has gone down with respect to the initial value, but we do get some non-zero value, and it's independent of time. The value is somewhere around 0.2 or something, and that value changes a little with respect to change in strength. But the important thing is that we have been able to remove the entanglement sudden death. And this can sometimes be useful if I am using the entanglement in this atom cavity system, in this atom photon system, for some gain with respect to some classical device. So yes, this is what I was talking about. It seems that disorder can wipe out entanglement sudden death, the phenomenon of entanglement sudden death. So we plotted this is essentially the same figure, but for a shown in a more objective way, so to say. So this sigma B is the strength of the disorder in the second atom cavity, and this is the strength of the disorder in the first atom cavity, and this is some type of an entanglement in the system, and there is some sort of a complementarity between the entanglement and so the higher amount of entanglement you give, it requires stronger and stronger amounts of disorder to wipe out the entanglement sudden death. Sorry, it's the opposite. So if you have high initial entanglement, then it only needs a small amount of disorder to wipe out the entanglement sudden death. So there is as I say, it's a complementarity. So if there is very high initial entanglement, then there's only a very small amount of disorder that is needed to wipe out the entanglement sudden death phenomenon. Questions, comments, or I will go to the.
Yeah, and this is sir. Okay.
Yes, yes, yes.
Yes, sir. I'm Shan speaking. So, what do you mean by this sudden death of entanglement? Do you mean that is the two cavities are disjoint or something like that?
Yeah. So the sudden death of entanglement is not something that we discovered. It was discovered by Everly, Wu, and a few other people. I'm forgetting the names. So this is the model that is there. You have to think of two cavities, and these cavities are being represented by as single modes of the electromagnetic field. And so these are very high finesse cavities. And inside each of those cavities, there is a two-level atom. Yeah, so I am considering some atomic system whose only two levels are in sync, so to say, with the frequency of the electromagnetic field that I am considering. And there is no atom-atom interaction, and there is no also cavity-cavity interaction. So you see that this is the first atom cavity, and this is the second atom cavity. So any entanglement that is there is the initial atom entanglement. So I'm initially preparing the system in this state, and I put some state for the cavities, and then I evolve. As I evolve, the entanglement behaves like. So let us look at this picture in which the atom photon strengths, interaction strengths are the same for both the cavities. The GA and GB are the same. This GA and GB appears here. You see, this is the atom photon interaction constant coupling. And what you see that as time goes by, there are points of points on the time axis. So, for example, here, and so on, where the entanglement suddenly comes to zero. By suddenly, what we mean is that if you take the derivative of this curve with respect to time, then there is a discontinuity. This is what is meant by suddenly. It doesn't, the derivative, I mean, it could have come smoothly, like it could have come like this to zero. It didn't come like this to zero. It comes like this straight. So mathematically, we understand this. Because this quantity concurrence is actually the minimum between 0 and another function, and that function is actually a continuous function, and it is also smooth, so it goes down and comes up. But because entanglement is a physical quantity that never becomes 0, one has to cut it off here, and you see this quantity. And it is mathematically well understood that if you take the minimum between two functions, one can land in non-smooth functions. So this is not a surprise mathematically, but physically we would expect physical quantities to be smooth. And this did not happen, and people called it as entanglement sudden death.
Okay, sir.
Any other question? Okay, so if not, I continue. Can you still hear me? Just to be sure.
Yeah, we can hear you.
Okay, thank you. So this is where I was, and yes. So as also in the previous picture, this response along with this complementarity retains some of the qualitative similarities, but differs widely in quantity for change of the disorder distribution. So, for example, this picture that I show you, if you change it to discrete disorder or to Cauchy-Lorentz disorder, the shape remains the same, but the exact quantity becomes very different. Yeah, so this is the reference, and these are the people who did the work. And this was last year. And yes, so we switch to a different subject while still staying with impurities. How much time am I left with?
time is already up, but okay, some problem happened. So you may take whatever you like.
Okay,
You can
so
go.
maybe I will try to quickly go through this. I'll take maybe 10 minutes or 5 minutes.
Yeah, it's fine. It's fine. You go ahead, please.
Yeah, I'll take 5 to 10 minutes. Okay. So we consider the same type of disorder, the glassy disorder, in something that we call a quantum random walk. It's there are some people who do not want to call this a quantum random walk, but a quantum walk because of certain technicalities. We will be calling with both the names. Yeah, so let me begin with the cartoon again. Everyone knows who's Johnny Walker, and he is with some drink, and he wants to walk home. Why am I showing you this picture? Well, this is what quantum walk is about, or any walk is about. So someone who is a drunk is trying to reach home, and he will reach home in a discrete number of steps. And for simplicity, we are considering a 1D lattice. Yes, so everything where the drunk can go along with the home is on a single straight line. And so at every step there are two options. The drunk can go forward or go behind. But being a drunk, the person tosses a coin at every site to decide the direction of the next step. So let's say if it's heads, then the person goes on the left, and if it's tail, then the person goes on the right. The correlation between head with left and tail with right is pre-decided, and we assume that the drunk remembers this. Okay. Now, if you consider such a real walker, a classical walker, and a coin, the walker will never reach home. What does it mean by he or she will never reach home? The meaning is that the position distribution of the drunk will become a Gaussian around her or his initial position. So it will have a peak around that initial position, and there will be a certain probability to reach home, but it will be very small if the home is significantly different from the initial position. Yes, so this is what we mean by a classical walker never reaches home. So this is what I wanted to say. And so the important point to notice here is that if you consider the variance of the classical walker's position, it is proportional to the square root of the number of steps. I would request you to remember this formula. This is very easy to derive. So the variance is proportional to the square root. So the point that I want to make is that if you go into quantum mechanics, then it helps. And this is not from us. It's known from quite a few years now, that you can show that if you consider a quantum walker and a quantum coin, then the coherence in the entire system and the entanglement between the walker and the coin leads to this. On the horizontal axis, there is it's a log curve. So on the horizontal axis, there is log of the number of steps. So capital T is the number of steps. On the vertical axis, it's the inverse of the standard deviation and the logarithm of that. And if you calculate this exact formula, then you will see that the variance is now proportional to the number of steps instead of the square root in the classical case. So in this sense, the quantum walker does reach home. So yeah, so as I said, the difference with respect to the classical Walker, sorry, did something wrong. So with the difference with respect to the classical Walker lies in the coherence in the Cohen state and the Walker state, and the entanglement between the Cohen and the Walker systems. And this is already known from, so, and there are a large number of papers in this area. Now we try to understand if there's disorder in the system, and I will quickly only tell you the result. What I will try to tell you is that if there is disorder, then the situation becomes sort of intermediate between classical and quantum. Now, there are many ways in which disorder can be inserted in the system, and we have considered a randomly distributed number of steps after every coin toss. So instead of one step after every one coin toss, we consider a randomly distributed number of steps after every coin toss. But the direction remains the same. Head, if left, so if head, the walker goes left. If tail, the walker goes right. And this disorder is assumed to be quenched. And if you do this calculation, you see, and you, on the horizontal axis is the same thing, but on the vertical axis is the same thing, but this sigma is replaced by the quenched averaged sigma. This is the only change. And again, you get a straight line, but the slope is different. So yeah, so this calculation is for the Poisson distribution. And if you do the calculation, you get, so the important thing here is this slope alpha, and that slope becomes 0.8. This was half for the classical case and 1 for the quantum case. So physically, I am in the quantum case, but if I introduce the disorder, then my exponent goes away from the quantum case, the ordered quantum case, towards the classical ordered case. So a little technically, this one can say it's super diffusive, but it's sub-ballistic. So you see, I mean, although quantum mechanics helps, if there will always be some disorder, and so you won't reach home. I mean, you will reach, but not so fast. And we considered, so that Poisson disorder was for the mean at 1, and we considered other values of mean. The scaling exponent doesn't change so much. And we did consider other non-Poissonian distributions also, some sub-Poissonian and some super-Poissonian. And the scaling does change a little, but not a lot. And this is these are the people who did these calculations. I presented only the first paper. I did not present this second paper. And this was for a walking on a circle. This was for walking on a straight line. This was for walking on a circle. So I will stop here. I will not go to the next topic. I'll just go to the last slide. So what I wanted to tell you is that impurities exist, whether you like them or not, and they can also be engineered. I didn't talk about this. I just mentioned it. And such systems are interesting in different ways. They can have interesting properties. They can tell us, they can point to interesting physical phenomena. And they can also sometimes be useful. And so that's it. Thank you. And this is the group, slightly old in our campus when meeting was allowed. And well, I'm waiting for times when such gatherings will become allowed once more.
Is this your group, Ujjwal?
Yeah, the quantum information group. There are 3 faculty members,
I see.
and the rest are PhDs and postdocs.
That's a pretty big group.
Yeah. Well, to be honest, there are some members that have moved and they had come to a conference. So maybe 3 or 4 or 5 maybe people who are at that point was not there in the group but had come. So just to be a little honest.
Anyway, so thank you, Ujjwal, for such a nice talk. It was very illuminating and at very, very pedagogical level. So it was very nice talk. So now forum open for a question.
Joel, can I ask you a question?
Yes, certainly.
So somehow I probably just missed a little in between, even after you've come back. So there has been a little bit of flip-flop on the role of disorder, in the sense that in the single Jains-Cummings model, you had seen that disorder helps to have a maximally entangled state.
Yes.
And for quantum information, say for example, the teleportation needs an a priori entangled state.
Exactly.
Now, later on, I think, I probably missed something. And later on, was it shown that disorder is detrimental for other things? Or am I...
You are right that so from the quantum information perspective, I think I did not show that in the Jains-Cummings model, I did not show that disorder is detrimental.
Okay.
So, yeah. So in all these cases that I showed here, disorder was actually useful from the quantum information perspective. If somebody wants to use the population inversion for something, then that, of course, is detrimental. The disorder is detrimental for that.
Okay.
But I mean, I just want to add here that there are plenty of other systems in which disorder is detrimental to entanglement. So entanglement does reduce in many other systems.
Okay. Yeah.
So can I ask you a question? Meaning, I don't know, I had difficulties with connection and all that, so I don't know if you have addressed this. But experimentally, from a practical standpoint, what is the current status regarding all these models and theories? I mean, have they been realized, for example, in the context of cold atoms or some other system and so on?
Yeah, the atom photon entanglement. This is, I mean, if you want to talk about in general quantum information, what has been realized, that is a separate topic. But if you want to restrict to the things that I have presented, this cavity QED experiments are, I don't know the details, but they are certainly very advanced now, much more than some years back. And one can have very high finesse cavities in which this Jains-Cummings model can be realized, not exactly, but to a very high degree of fidelity. And in general quantum information, things are much more positive if you look at quantum communication. So there the main horse, so to say, is our photonic systems, and that is quite advanced now, and one can have cryptography from satellite to Earth and so on. Whereas the other main advertisement of the subject, which is quantum computation, that is certainly not very advanced. There are some players in the market, quite big ones, but still we are far from what a classical computer can compute for us.
Okay. Yeah. So regarding quantum communication, so I heard that China has already developed some such communication networks and so on. So what is the status of India vis-a-vis this quantum communication networks and so on? I mean, I don't know if that's a relevant question for this talk, but just like offhand.
Yeah, I mean, it's. I mean, of course, the chair can consider whether it is relevant, but I mean, I would think that it is, and well, the Indian status in this entire subject is not very strong if you compare with other countries. And certainly with respect to the experimental status in this country and the experimental status of the neighboring country of China, it's not very good. There are certain groups in India who are trying to build quantum communication devices. There is one group in RRI, there's one in IIT Kanpur, and there is one in Ahmedabad, and there are several others that I'm missing. And so they are advancing. They are being not an experimentalist. I am slightly so to say, a bit reserved in saying the exact relevance of the works that are being done in this area. But I'd say that things are advancing, but not up to the mark as yet.
Okay, thank you.
Okay, any other question? So, Ujjwal, can I ask one question here?
Yes.
Here you show the effect of disorder that basically brings it to the more and more entangled state. Yeah. So if I look at all these things from the nonlinear point of view, what I see that initially it was the bit kind of oscillation, and then slowly the disorder kills that the time-dependent behavior, and it brings it to some static state.
Exactly.
So from that point of view, can we basically see some sort of the role of disorder here to kill that kind of time-dependent behavior, and can find out some sort of bifurcation diagram that can get some cutoff or some threshold value of disorder beyond which we'll get entanglement and
yeah, I mean, we have indications to that, certainly, but all these are numerical indications. Now, we don't have an analytical answer to your questions, but we do see. So if you look at this picture here, you see that there is some threshold after which the oscillations vanish, and both in the entanglement diagrams and in the population inversion diagrams. But these are still numerical calculations. So we showed also this picture later on, this one, where we wanted to see what happens to the entanglement sudden death as you go to higher and higher disorder. But that again depends on the type of disorder. Whether it's Gaussian disorder or it's Cauchy-Lorentz, it changes.
I see.
Okay. So yes, there is this thing that you are talking about. There is the beats are going away because of the introduction, but we are not getting that classicality.
Okay.
It somehow keeps the quantumness in the system.
I see. Okay. So thank you. So any other question from a student side? Kanaya?
No, I do not have any question. It's fine. I was also a bit busy with some kind of presentation I have to make. So
Okay.
I was a bit diverted.
Okay. So Saurabh? Okay. So if there are no further question,
I'm done. Thank you. Thanks a lot, Ujjwal. Thanks a lot. Very nice talk. It was
Thank you very much.
very simply told and nice. Thank you very much.
Thank you.
and
Thank you very
definitely we would like Ujjwal to visit sometime here.
Yes.
Certainly.
Absolutely.
You are all invited
Absolutely.
once this pandemic recedes. You are all invited.
Yeah. Sure.
Okay.
Yeah.
Thank you.
Okay.
All right.
Thanks a lot, everyone. Okay.
Okay. Bye.
Thank you very much.
Bye.
Bye.